Alright folks, welcome to another video on electric machines and controls and modeling electric machines and drive systems using MATLAB Simulink. Uh, so in the past we have gone through different variations of modeling techniques using MATLAB and Simulink, and I hope you had a good exposure, good experience through this sequence of videos. And this will be the last of this series of videos that uses MATLAB and Simulink. Unless there are additional topics, I'm planning to go into a different set of topics because I have different video requests. And if any of you are interested in other topics, feel free to send me an email or put it down in the comments, and I'd be happy to include that in my future videos. Now, to recap, last time we talked about how we can integrate or develop the dynamometer in our simulation here. So we looked at implementing the mechanical dynamics, the DC motor, and then the controller aspects of it to see what that brings into the picture. And we have our model that we have been working on for field-oriented control. And then we have our dynamometer setup that performs the speed regulation, right? And I hope all of you had an opportunity to build this yourself and test it out. Today, we're going to be focusing on the inverter part, and I'm not going to spend a whole lot of time on this, but we'll go over that and hopefully you'll be able to implement this yourself. In the previous models, we used just a voltage source, an ideal voltage source that follows the reference, which gave us very nice waveforms. So if you to go and observe these current waveforms, you can see that they are very nice and smooth and they are ideal, right? So sometimes ideal results help validate the concept, but practically you'll need to be a little bit more flexible because your results are not going to look that perfect. So in order to capture some of those non-idealities, we can actually add an inverter model into the simulation component and make the data look more realistic, or at least you'll be able to see some of the discontinuities and some of the noise signals that are arising in such a inverter based system. So that's the goal of this video. Now looking at the parameters, they are the same parameters, the machine parameters that we used in our prior simulation, so nothing changed. And the only change as we go through this simulation is in the inverter part, and that's again only on the PMSM side, not on the DC motor side, because you can follow the same concepts that we are going to be talking about and implement an H-bridge on the DC motor side for the speed regulation part of it. Okay, all right. So first things first, keep in mind when you add this inverter, it's gonna run your simulation quite slower, and that depends on your computer performance too. But if you have already a slow computer, adding this inverter model is gonna slow it down quite a bit. Okay, so I'm going to walk all of you through the different elements that we have here. So this is our inverter that we have. These are the same references that we fed to our ideal voltage sources. And here what we are doing is we take those reference ABC voltage reference signals and we convert them to PWM signal. Okay, PWM signal. And in order to do that, we have this PWM generator block in MATLAB. It's the 2-level PWM generator. So when you go inside, you want to select the 3-phase 6 pulse setting here from the drop down and make it unsynchronized, and then set the frequency for the carrier to be 10 kilohertz. And then you can set the initial phase to be 90 degrees and the minimum maximum value to -1 and 1. and then your PWM frequency has to be quite high. So 1E minus 6 is a reasonable PWM frequency. So you're going to have to set those, and then what will happen is, since this is a 6-channel output, your output coming from the PWM generator will have 6 signals. So you will need to demultiplex those 6 different signals, and you're gonna put them or apply them onto these labels. These are go-to labels, and then these are from labels. Okay, these help in making your Simulink model cleaner. So you're gonna apply these go-to signals, go-to labels to the 6 signals, and then you're gonna place them to each of these MOSFETs. So for each leg, for each phase, has 2 MOSFETs here, right? And these are the same MOSFETs that you have in your sim power blocks. You're gonna have 6 switches, and you're gonna apply these labels to each of them, and then you can have these connections going into each of the phases. Okay, and then if you are comparing this with a experimental setup, and let's say you have a 40-volt system, you will want to split the voltage into 2 sources so that you can have this neutral point set up here. This will help in solving this system. It sometimes it works, but sometimes it'll throw an error. So I typically set this up just in case, and there's no harm done in doing that. So now you have implemented your model. Okay, now in case you want to change the parameters, you do have some flexibility within the MOSFET to change some of the parameters, so you can test different configurations. So feel free to do that, and you can try to match some of your experimental setup based on or by changing these parameters. And of course, we talked about how to set the motor parameters in the previous video. And we're going to be measuring the inline or the phase currents that are applied to the motor. In practical applications, you tend to have low side or high side shunts. You can apply the same. You can place a resistor or place a current sensor on the low side or high side, and then you can measure those voltages, then use them for your control as well. I'm not going to go into that because that adds a level of complexity to your simulation. So I'll leave that up to all of you to investigate. And doing phase measurements are easy, but when you go into the hardware point of view, that gets complicated. So that's why people tend to go into low side or high side shunts. Okay. All right. So we have our current measurements, and then those current measurements are going to have noise. So you're going to have to filter them out. So I have a 500 hertz low pass filter here, first order low pass filter, that's eliminating some of the noise for us. Okay, so that's one topic, one point here to note, that we didn't have this filter in our previous models. Now, another thing to keep in mind is when you are looking at an embedded system that's driving a PMSM, they are executed, those systems, the field-oriented control algorithms are executed at the PWM intervals. Okay, but in this model, it's a little bit different. Unless you specifically implement a discrete control system from here going forward, this will be a continuously executing model. Okay, and again, that is done the way I done that here is for simplicity, because otherwise you'll have to implement a discrete time controller, then trigger it based on your PWM signal, and that again adds more complexity. Okay, so to keep things simple, I've actually developed this basic, very simple model. But if you are interested, you're free, feel free to modify them to be edge. Use a trigger to trigger these blocks, and then use a specific sample, and then process the field-oriented control algorithm based on that, which is closer to what the real system is doing in real life. Okay. All right, so now we have our currents. So those are filtered. They are applied to the the controller, and they go through the transformation, they get fed back, and now you have your closed loop feedback control system that has an inverter in place. Okay, now another small change before you continue or try to run your model, you will want to go to your settings, your model settings, and then change your step size 1e to 1e minus 6 to match with your PWM frequency. Okay, otherwise you're going to have issues because the sampling times are not matching. It'll throw an error. So just note that when you run your simulation. And now you'll see that when we run this, it's going to take a little bit of time than usual. See, it's running very, very slow compared to previous times where we didn't have this inverter model, and partly this is due to our sampling rate being much smaller, 10 times smaller than before. Okay, so if you make this a discrete time system, it'll even take a little bit more time to execute a higher number of samples. But we can monitor our currents here. You can see we are experiencing, or we are seeing quite a bit of noise, which is different from what we saw in the previous time. However, you can still see that our IQ is regulated close to our reference. I mean, it's very close to around 2 amps. And then we do have quite a bit of noise on ID. And then you can filter this out if you'd like to. Okay. All right. So that's the IQ. And then if you're interested in looking at your phase currents, you can look at your phase currents here. Okay. You can see your phase currents. And again, what you can do is you can even add different modulation strategies. You can add different modulation strategies to generate PWM signals and apply it to the inverter. You can try space vector. You can try discontinuous PWM rather than just trying, sine triangle type of a PWM approach. Okay, so those are different variations that you can try, but this, I hope, help you understand how to implement a three-phase inverter using MATLAB Simulink blocks, and now you have a comprehensive PMSM torque control model that uses current references to control torque, and then you have a dynamometer regulating speed at the other end. Okay, I hope all of you enjoyed this series of videos, this sequence of videos, and then I'm hoping to add more content as we go through. So please feel free to let me know if there are any topics in machines and drives that you'd like to see me do a video on. Okay. All right, folks. Thank you. I'm going to wrap this up